Welcome to Lesson 1.1 Introduction to Fine-Tuning Learning Objectives. By the end of this lesson, you'll be able to define what fine-tuning actually is, not just the buzzword, but the real mechanics. You'll know which problems it solves brilliantly, which problems it handles poorly, and exactly where it sits on the spectrum of ways you can adapt a language model. That last point matters more than most people realize, and it'll save you from burning weeks on the wrong approach. What is fine-tuning? Fine-tuning is the process of taking a pre-trained language model and giving it additional specialized training to make it better at specific tasks or behaviors. Here's the analogy that makes this click. A base model like Llama 3 or GPT 3.5 is like a new university graduate, sharp, well-rounded, capable of reasoning through almost anything. But if you need them doing cardiac surgery or arguing a patent case, you need to train them further. Fine-tuning is that specialized training. The difference from just prompting the model is fundamental. Fine-tuning bakes knowledge directly into the model's weights. The capability becomes part of the model itself, not something you have to explain every time you open a conversation. Concretely, when you fine-tune a model, you're doing one or more of four things. You're adding new knowledge, domain facts, specialized terminology, expert reasoning patterns. You're teaching new behaviors, a writing style, a personality, a specific tone. You're sharpening performance on specialized tasks, things like medical diagnosis or legal analysis, where the base model is competent but not expert. Or you're changing the shape of responses, the format, the structure, the level of detail. Each of these is a legitimate reason to fine-tune, and we'll see real examples of all four throughout this course. Fine-tuning has real limits worth understanding up front. Knowledge gets frozen at training time. If the world changes, the model doesn't automatically know. Updating a fine-tuned model means retraining it, which isn't free. And for information that changes constantly, stock prices, live news, rapidly evolving documentation, fine-tuning is the wrong tool entirely. That's exactly the problem retrieval augmented generation, RAG. Knowing this boundary now will stop you from architecting yourself into a corner later. Why fine-tune? Here's the landscape shift that makes this the right moment to learn fine-tuning. Through 2024, the gap between top closed-source models like GPT-4 and the best open-source models narrowed dramatically, driven by releases like Meta's Llama 3.2 and the wave of models from Mistral. That gap matters because it changes your economics completely. You can now take an open source model, fine-tune it for your specific use case, deploy it wherever you want, your own server, a cloud VM, a local machine, and pay no API costs, hit no rate limits, and maintain full control over your data. That combination wasn't really practical 2 years ago. It is now. Two examples show how domain expertise fine-tuning works in practice. A hospital needs AI assistance with medical imaging. Base GPT-4 can read images, but it wasn't trained to recognize the subtle patterns a radiologist looks for in an MRI or CT scan. Fine-tune on a curated medical imaging dataset, and the model learns to identify those patterns with diagnostic accuracy. The second example, legal document analysis. Default models don't understand jurisdiction-specific case law or the precise language that determines whether a contract clause is enforceable in your state. Fine-tune on relevant case law and legal documents, and you get a model that reasons about precedent the way a trained attorney does. Personality and style transfer is one of the most underrated fine-tuning use cases. Suppose you want an AI assistant that's genuinely sarcastic, or that writes with the measured, aphoristic style of Paul Graham. Prompting gets you maybe 80% of the way there. The model will try, but it won't be convincing. The reason is that authentic voice is woven through thousands of subtle choices: word selection, sentence rhythm, what gets left unsaid. Fine-tuning on a corpus of someone's actual writing, speeches, and interviews captures those patterns at the weight level. The model isn't performing the style, it has internalized it. That's the difference between a convincing impression and a genuine voice. Two more use cases that are harder to solve with prompting alone. First, structured output generation. Production systems that parse model responses into JSON or feed them into downstream APIs need the format to be correct every single time. Prompting gets you close. Fine-tuning makes it reliable. The second is creative tasks, generating ASCII art, writing in a specific poetic form, producing output with a particular aesthetic quality. The challenge is that beautiful or elegant is nearly impossible to specify in a prompt. Fine-tuning on curated examples teaches the model what you mean by showing it, not telling it. Cost reduction is one of the most compelling practical arguments for fine-tuning, and the math is straightforward. Start by running GPT-4 in production. High quality but expensive. As you accumulate user queries and GPT-4 responses, that interaction history becomes a training dataset. Fine-tune Llama 3.8b on that data, and you get a smaller model that has learned to replicate GPT-4's quality on your specific use case. Switch your production traffic to the fine-tuned 8b model. The result is roughly 10 times lower inference cost with comparable output quality for your domain. You use the expensive model to teach the cheap one, then retire the expensive one. Real-world examples. Consider a hospital deploying AI to assist with symptom triage and diagnostic suggestions. The base model problems are stacked. Medical terminology is underrepresented in general training data. The model needs to follow specific diagnostic decision trees. Output must be structured for integration with an EMR system, and there are legal requirements around audit trails. The solution is fine-tuning on medical textbooks, anonymized patient case studies, diagnostic flowcharts, and the hospital's own protocols. Each of those data sources addresses a specific gap: terminology, reasoning process, output format, and institutional compliance. A company deploying a customer support AI faces a different but equally concrete set of problems. The base model doesn't know the company's products, internal jargon, or pricing policies. It has no concept of brand voice. It will happily answer questions it should escalate or refuse, and it can't improve from real customer interactions unless you train it to. Fine-tuning on historical support conversations, product documentation, a style guide, and escalation protocols solves all of these at once. The result is a model that sounds like your company and knows when to say, "That's outside my scope." An author wanting an AI writing assistant presents a subtler challenge. Writing style isn't a setting you can dial in. It's the accumulated effect of thousands of micro decisions about word choice, sentence length, paragraph rhythm, and narrative voice. Describing it in a prompt is nearly impossible because the author themselves may not be able to articulate what makes their writing theirs. Fine-tuning on the author's existing books, journal entries, correspondence, and outlines gives the model direct exposure to the patterns. It learns by example what no prompt could adequately describe. When not to fine-tune. Fine-tuning is a powerful tool, but reaching for it by default is a mistake. There are 4 situations where it's the wrong choice, and recognizing them early will save you significant time and compute. The first is frequently changing information: stock prices, breaking news, weather, rapidly updating documentation, anything where the ground truth shifts faster than you can retrain. Fine-tuning freezes knowledge at training time. For dynamic data, RAG is the right architecture. It retrieves current information at inference time rather than encoding stale facts into weights. The second is insufficient training data. Quality fine-tuning typically requires hundreds to thousands of examples. If you have 10 to 50 examples, you don't have a fine-tuning data set, you have a few short prompting is faster, cheaper, and often just as effective at that data scale. Start there and only consider fine-tuning once you've accumulated enough examples to justify it. The third is tasks the base model already handles well. If GPT-4 or Claude already produce the output quality you need for general questions or common tasks, adding a fine-tuning step introduces cost and complexity with no meaningful gain. The right call is to use the base model via API and spend your engineering time elsewhere. The fourth is when you need explainability. Fine-tuned models are black boxes. The reasoning is distributed across billions of weights, and there is no audit trail for why a specific output was produced. In regulated domains where you need to show your work, rule-based systems or RAG with source citations give you the traceability that fine-tuning fundamentally cannot. Key takeaways. 5 things to carry forward from this lesson. Fine-tuning embeds knowledge into model weights. That's architecturally different from RAG, which adds context at inference time. The open source model quality gap has closed enough to make fine-tuning genuinely practical without depending on proprietary APIs. The strongest use cases are domain expertise, personality and style transfer, specialized tasks, and cost reduction by distilling expensive model behavior into cheaper ones. The weakest use cases are frequently changing data, small data sets, tasks the base model already handles, and anything requiring explainability. And the graduate analogy is worth keeping. Base models have the fundamentals. You're giving them the specialization. Check your understanding. 5 questions to test your understanding before moving on. First, what analogy describes base models in this lesson? Base models are like new university graduates, strong fundamentals, but needing specialized training for specific roles. Second, name 3 use cases where fine-tuning excels. Any 3 of these count. Domain knowledge, personality and style transfer, specialized tasks, structured output, cost reduction, behaviors that resist prompting, or creative tasks. Third, why is fine-tuning a poor fit for a news chatbot? News changes in real time, and fine-tuning freezes knowledge at training time. Constant retraining would be required, making RAG the better architecture. Fourth, how does fine-tuning reduce costs versus GPT-4? Collect GPT-4 responses on your use case, fine-tune a smaller model on that data, then run the smaller model in production at a fraction of the inference cost. Fifth, true or false. You can update a fine-tuned model's knowledge by asking it questions. False. Knowledge lives in the weights and can only be changed by retraining. For dynamic information, use RAG. Reflection exercise. Before moving on, take 5 minutes to write down answers to these questions about your own project. What problem are you trying to solve with AI? Does it require specialized knowledge or behavior that the base model lacks? Does the relevant information change frequently? Do you have access to at least 100 training examples? And based on what you've learned here, should your solution use fine-tuning, RAG, or a combination of both? Keep these notes. You'll return to them throughout the course, and by Module 7 you'll have everything you need to actually build it. Assignment. Before moving to the next lesson, pick a project direction. Domain expert bot, medical, legal, or technical. Personality transfers, celebrity style or brand voice. Creative tasks, writing or art generation. Structured output, JSON, SQL, or code. Translation and multilingual applications, or something else entirely. Describe it in your own words. You don't need to commit permanently. You need a direction to make the exercises concrete. You'll refine and implement this project in Module 7. Next lesson. You now have a clear mental model of what fine-tuning is, what it's good for, and where it breaks down. The natural next question is, how does it compare to RAG, and how do you choose between them for a real project? That's exactly what Lesson 1.2 covers, the RAG versus fine-tuning decision framework. It's a practical decision tool you'll use throughout this course and beyond. This diagram shows the three-stage arc of fine-tuning. You start with a pre-trained base model, built on trillions of tokens of general knowledge, giving it broad reasoning capability. That model then passes through fine-tuning, where you apply your own task-specific training data, typically somewhere between 1,000 and 100,000 examples. That training step adjusts the model's weights to concentrate its capability on your domain. The output is a specialized model that performs your target task at expert level. The key insight here is the data volume range, 1,000 to 100,000 examples. That's the practical window where fine-tuning is worth doing. Below that, few-shot prompting is more efficient. Above that, you're approaching pre-training territory. Knowing where your dataset falls in that range will shape every decision you make in this course. This diagram maps fine-tuning use cases across industries, and it's worth pausing on because it reframes fine-tuning from an abstract technique into a concrete engineering decision. In business, customer support chatbots and email drafting assistants represent high-volume, repetitive tasks where consistent quality and brand voice matter. In legal and finance, contract analyzers and financial report summarizers handle dense, specialized language that general models. Healthcare applications, clinical note summarization, drug interaction lookups require both domain accuracy and structured output for integration with clinical systems. Developer tools like code review bots and docstring generators operate in a domain with its own syntax and conventions. Content tools like brand voice writers solve the style consistency problem we discussed earlier. Notice the pattern. Every one of these use cases involves either specialized language, consistent behavior, or structured output. Those are the three signatures of a good fine-tuning candidate. This diagram shows the LLM adaptation spectrum, and it's one of the most useful frameworks you'll take from this lesson. On the far left, prompt engineering and few short examples. Zero cost, minutes of work, but limited headroom for customization. Moving right, retrieval augmented generation, which takes days of setup and around $100, but handles dynamic data elegantly. Then fine-tuning with LoRa, the method this course teaches, which typically runs $10 to $100 and takes days rather than weeks. That's the sweet spot, meaningful model customization at a cost that's accessible for individual developers and small teams. Further right, full supervised fine-tuning runs into the thousands of dollars and takes weeks. Pre-training from scratch costs millions and takes months. Understanding where LoRa fine-tuning sits on this spectrum tells you exactly what you're signing up for: significant capability gains at a fraction of the cost of the alternatives to its right. This diagram is your roadmap for the entire course. The fine-tuning workflow has 6 stages. First, choose a base model, Llama, Mistral, Gemma, or others. Second, prepare your dataset. Format, clean, and validate it to match what the model expects. Third, configure LoRa, set the rank, alpha, and target layers that control how and where the model gets updated. Fourth, run training using the SFT trainer from Hugging Face combined with the Unsloth library for efficiency. Fifth, evaluate, test outputs, run benchmarks, and verify the model actually learned what you intended. Sixth, deploy, export to GGUF format, serve via API, or run locally with Ollama. Each lesson in this course maps to one of these stages. By the time you've completed the full sequence, you'll have walked this entire pipeline end to end with a real model on your own hardware. This diagram extends the use case map across 6 sectors, and the breadth here is intentional. It's meant to help you locate your own project within a space that's already proven. Healthcare, clinical note summarization and drug interaction checking, where accuracy directly affects patient outcomes. Legal, contract clause extraction and compliance checking, where precision in language. Customer support, ticket routing and FAQ auto response, where volume and consistency are the core problems. Software development, code completion and bug triage, where the model needs to reason about syntax, logic and intent simultaneously. Finance, earnings report summarization and risk flag detection, where the model needs to extract signal from dense, structured prose. Education, step-by-step math tutoring and personalized quiz generation, where the model needs to adapt its output to individual learner needs. The common thread is that each application requires the model to operate with a level of domain specificity that general prompting can't reliably deliver. Before you commit to fine-tuning, this framework gives you 4 checkpoints to work through. First, can better prompt engineering solve this? Zero-shot and few-shot examples handle a surprising range of tasks, and they cost nothing to iterate. Second, is this a dynamic data problem? If the information changes frequently, RAG is almost always the right answer. It's cheaper to update and doesn't require GPU time. Third, would a larger base model close the gap? Moving from a 7B to a 70B parameter model can deliver the reasoning capability you need without any training cost. Fourth, can system prompt tuning get you there? Adjusting persona, output format, and behavioral constraints in the system prompt is fast to iterate and often underestimated. Work through these 4 checks before opening a training script. Fine-tuning is powerful, but it's also the most expensive option on this list, and it's only the right choice when the cheaper options have genuinely run out of headroom.